If you book a trip on Amtrak today, the experience feels entirely seamless. You download a digital ticket, track your train's progress in real time, and scan a QR code. The customer-facing side projects an image of modern, cloud-native efficiency. But underneath that polished interface, none of this operates on the cloud. The entire digital ecosystem routes back to a legacy system called Arrow. Launched in 1981, Arrow is built directly onto an IBM transaction processing facility mainframe. Processing data is only half the equation. The physical, tangible logistics of moving locomotives through congested corridors requires entirely different operational technology. That reality is controlled by CTEC, the Consolidated Electrification and Traffic Control System, which manages physical track switches and balances power grids. Amtrak keeps this aging hardware alive out of strict operational necessity. The IBM TPF mainframe was engineered for pure speed. It processes millions of concurrent passenger transactions in sections of a second. If a dispatch query drops, the actual trains stop moving. Near-zero latency is a hard requirement. Instead of replacing that core, engineers build modern API wrappers and analytics databases around it. Every slick new mobile app has to reach through layers of modern code to pull raw data from a 1980s foundation, leaving the core tightly locked in the center. This creates a structural trap. The new systems depend so heavily on the legacy data streams that extracting the central mainframe directly threatens the minute-by-minute operational survival of the moving steel on the tracks. Amtrak actually attempted to escape this trap in 2009. They launched a fully funded project called ResNG, explicitly designed to shut Arrow down for good. The project collapsed completely, spending millions without finishing half the planned software modules. Arrow is tethered to thousands of points across the system. Pulling that central node out without a perfect transition mechanism causes the entire network to cascade into darkness. This outlines the enterprise architect's dilemma. How do you modernize a tightly coupled, mission-critical cyber-physical system without halting operations? You have two paths. Option A is a brownfield migration strategy. This involves painstakingly untangling the old code and migrating it module by module into modern microservices while the system remains live. Option B is a greenfield rebuild strategy. You bypass the technical debt entirely, building a brand new architecture from scratch to eventually replace the legacy system in one major cutover. Navigating this choice requires an evaluation of software frameworks alongside the capital and operational trade-offs of integrating IT data streams with physical, operational technology safety systems. This architecture diagram shows the target state for the Option A migration strategy. Notice the strict division. Arrow handles the passenger data on the left, while CETC manages the operational control on the right. In this target state, Arrow moves off the mainframe entirely. It relies on event-driven Kubernetes microservices and Kafka data streams to handle high-volume reservations and dynamic AI pricing. Over on the CETC side, the system shifts to a cloud-native architecture utilizing a digital twin. This creates a real-time simulation of the Northeast Corridor for predictive dispatching and energy optimization. Connecting them is a zero-trust security bridge. This is critical to ensure that passenger IT data can interface with track-level OT data without exposing the physical trains to cyber vulnerabilities. To reach this state without dropping a train, engineers deploy the Hybrid 7R strategy, a phased approach of rehosting, refactoring, and rebuilding over several years. This relies heavily on the Strangler Fig architectural pattern. You run the new cloud services in parallel with the mainframe, routing traffic to the modern system and slowly strangling the legacy modules one by one until they can be decommissioned. The massive bottleneck in this process lies in the physical world. Any changes to the CETC control side require rigorous Federal Railroad Administration safety certifications to prove SIL 4 level reliability, which drastically extends the timeline. The financial toll for this untangling process is steep. Current estimates place the migration cost between $220 and $280 million over 4 to 5 years of parallel execution. The Strangler Fig migration mitigates immediate catastrophic failure risks, but it accomplishes this by shackling the organization to a half-decade of agonizingly slow parallel operations. Option B offers a radical alternative, the Amtrak Cognitive Rail System, or ACRS. This is a clean slate greenfield build designed to avoid legacy technical debt. This document outlines the pre-design evaluation. Before architecting the ACRS, engineers audited advanced international rail systems. They evaluated China's CRIMS platform, noting its massive transaction volumes and use of AI for dynamic scheduling and biometric ticketing. They looked at Japan's Cosmos system, which provides exceptional punctuality through zero-latency real-time control, and Germany's DB Navigator, which excels in multimodal integration through flexible open APIs. Titan Software extracted the core mechanisms from these proven models and combined them into a single, unified North American architecture. The greenfield approach represents a shift in engineering philosophy. Instead of spending millions to update the architecture of the 1980s, you design a system that imports the global standards of the present. This diagram presents the blueprint for the Amtrak cognitive rail system, separating operations into functional layers. At Layer 0, the interface incorporates AI biometrics inspired by Asian rail implementations. This eliminates traditional paper and mobile QR codes. The passenger's facial or voice identity is verified at station entry, mathematically converted into a cryptographic JSON token, and used directly as the ticket. Below that is the cognitive backbone, utilizing Microsoft Azure for AI services, connected to Oracle Cloud Infrastructure for heavy database tasks. At the bottom, the Edge Safety Network pushes real-time control to edge hardware built with highly secure Rust and C++. By pushing safety-critical compute directly to the physical edge, ACRS ensures that even if the central cloud experiences an outage, the trains on the tracks continue operating safely. This meets the zero downtime mandate without relying on a centralized mainframe. This table directly compares the projected outcomes of the two strategies, placing the new build and the migration side by side. First, look at the timeline. Both projects require approximately 4.5 years to complete. The clean slate build doesn't save time because the primary bottleneck is universal. Software development is fast, but safety testing hardware-in-the-loop systems for moving physical steel takes years of regulatory validation. But the budget reveals a sharp contrast. The Greenfield ACRS project is estimated at $245 million, making it highly competitive with the migration strategy, which could stretch up to $280 million. The true divergence happens in the total cost of ownership. Because the Greenfield model severs the mainframe entirely, it projects a 60 to 75% reduction in ongoing operational costs over 5 years, vastly outperforming the migration's incremental savings. The data shows that the Greenfield approach provides superior capabilities and better long-term cost efficiency. The final decision rests entirely on institutional risk tolerance. The brownfield migration path offers a safer start by running systems in parallel, but it guarantees years of retaining technical debt and wrestling with legacy constraints. The Greenfield path gives you a clean, modern baseline and advanced biometric capabilities, but it requires a massive, high-risk cutover event to transition operations all at once. This architecture governs the kinetic energy of heavy passenger rail moving across the continent. A failure in data synchronization translates directly into stopped trains. Engineers must choose: meticulously untangle the tangled logic of the past, or boldly build the architecture of the future from the ground up. Building shiny mobile apps layered on top of old hardware is trivial. The true frontier of enterprise engineering is executing a safe extraction of an outdated core without bringing the physical world to a halt.